Hello, and welcome to the last day of the physics webinar series. I am Jonathan P. Maligo, and I will be your instructor for today. So for this day, we will be having a crash course on emission spectroscopy. So we are still on our webinar series on spectral analysis and measurement. So emission is basically the giving off of light by a material, and spectroscopy is the study or analysis of the light emitted by a material. So without further ado, let's now start this course. So light is an electromagnetic wave, but it's also a particle called a photon. So light is actually both a wave and a particle. And in fact, everything is actually both waves and particles. So even us, even though we are particles, we also have wave characteristics, but we will not focus on that today. So this is the electromagnetic spectrum. This basically refers to the range of wavelengths of light. So the only light that is visible to our eyes, which is what we call the visible region, comes from or stems from red to violet. So this is the only region of light that is visible to our eyes, from red to violet. Below red, that's usually a much lower energy. You have infrared, and then much lower than infrared, you have microwaves, and then you have radio waves. So radio waves has the longest wavelengths. Its wavelength, the length between these two wave crests, is actually comparable to buildings for radio waves. For microwaves, it's comparable to butterflies. Infrared is comparable to a needlepoint. Visible light wavelength are comparable to protozoans. UV light wavelength are comparable to molecules, and the wavelength of gamma rays are comparable or in the same size as the atoms or the nucleus of atoms. So going to the right, this is actually decreasing wavelength but increasing in energy. So the gamma rays are the most energetic forms of light. So when we see color, that's actually one wavelength of light. So in the visible range, usually red is around 700 nanometers. It has a longer wavelength as compared to violet, which usually has a wavelength of 400 nanometers. But again, lower wavelength means higher energy. So the visible light is from red, 700 nanometers, to violet, 400 nanometers. So in our discussion, we will focus only on the emission of light without heating, and we usually call that luminescence. So emission of light from a cold source, not from a hot source. So energy is, in the concept of emission of light, energy is actually absorbed and then emitted or re-emitted again by the material. So in this case, instead of using the wave picture of light, instead of discussing about reflection, refraction, the wave properties of light, we will be talking about absorption and emission, the particle picture of light, absorption and emission. So in contrast to luminescence, incandescence is the emission of light by heating due to high temperatures. So incandescent light bulbs, for instance, the old light bulbs before the era of LED bulbs, you have incandescent light bulbs, the yellow ones. They emit light by heating the filament of the light to a very high temperature. So that's incandescence. So self-luminous objects are objects that produce their own light. So example of that is the sun. Even though the sun is primarily emitting light by virtue of incandescence by heating to high temperatures, but we will still refer to it as a self-luminous object because it produces its own light. A firefly's what do you call abdomen? A firefly's abdomen, for instance, is also a self-luminous part of the firefly because it can emit light on its own. So non-luminous objects are the rest of the objects. So they reflect light from self-luminous objects. So example is the moon. The moon is a non-luminous object. It just reflects light from the sun towards our eyes. So for also the human body and anything is all are referred to as non-luminous object because we don't emit our own light. So the reason why you see me is just because of the diffuse reflectance from the natural light that is reflecting from my body. So diffuse reflection or diffuse reflectance is actually the reason why we see everything. So the reason why you see me right now is because of diffuse reflectance. So without light, you cannot see me. So I'm a non-luminous object. Without light, I'm invisible or I'm just black. You will see nothing but black without light. So we will discuss some examples of luminescence, but we will just limit our discussion to some types of luminescence. So one type is called thermoluminescence. This is emission of light by minerals and some crystalline materials after absorbing heat. So take note, this is not a property of all materials, but only for minerals and some crystalline materials after absorbing heat. But the heat that is absorbed is not similar to incandescence, where incandescence usually results in a very high temperature. In thermoluminescence, is not. So that's the difference between thermoluminescence and incandescence. So usually these materials have previously absorbed high energy light or ionizing radiation. That's the reason why they glow when you apply a small amount of heat to them. So another type of luminescence is electroluminescence. So from the word electro, this is emission of light upon application of electrical current. So examples of these are LED lights, neon signs. So they all electroluminous, or they are all electroluminescent. So another type of luminescence is chemiluminescence, so emission of light due to chemical reactions. An example of this is the glow stick. So in a glow stick, there are actually two separate types of chemicals. And when you break the glow stick, you actually mix this chemical, and this mix creates a chemical reaction which leads to the emission of light via chemiluminescence. So bioluminescence, on the other hand, is just a type of chemiluminescence, which is chemiluminescence produced by living organisms. So example of that are jellyfish and fireflies. So bioluminescence. So another type of luminescence is photoluminescence. So unlike thermoluminescence, which uses heat, and electroluminescence, which uses electrical energy, and chemiluminescence, which uses chemical energy, photoluminescence uses light energy or emission of light after absorbing light. So you use light to emit light. So a specific type of photoluminescence is what we call fluorescence, wherein the emission of lower energy light is observed after absorbing high energy light. So example, if you illuminate your fluorescent material with UV, and then your material emits visible light. So lower energy light and visible light as compared to UV. Take note, UV is higher energy as compared to visible light. So example of this are fluorescent light bulbs. So inside a fluorescent light bulb, there's actually a gas there containing mercury actually. And basically what happens first is electroluminescence. So you apply electric current and the gas actually electroluminesces. They emit UV light. So there's actually UV light inside your fluorescent light. And your fluorescent light actually has a white coating. That's actually a phosphor coating. And this phosphor coating, when UV light hits this phosphor coating, it actually emits visible light. So hence the term fluorescence. So the phosphor coating in the light bulbs absorbs UV light, and then it emits visible white light. So another example of fluorescent materials are quantum dots. So this is a colloidal quantum dots that are suspended in a colloid or a liquid. So this is without illumination with UV, but when you illuminate it with UV light, you will notice that it will emit a brighter, uh, maybe a different color and a brighter light. So this is photoluminescence called fluorescence. So in this case, the material absorbs UV light and then it emits a lower energy light, a visible energy light. So one advantage of quantum dots is actually they can be programmed to emit different uh, visible light in different wavelengths of visible light. That is why one application of quantum dots is in TVs. So I think Samsung already has quantum LED TVs, quantum dots LED TVs. So they use blue light to excite quantum dots to emit red and green. So you will now have RGB or the primary colors, red, green, and okay. So what actually happens when a material absorbs heat in the case of thermoluminescence, or it absorbs chemical energy in the case of chemiluminescence, or it absorbs electrical energy in terms of electroluminescence, or it absorbs light in terms of photoluminescence. So what happens is the molecules and atoms of that material are actually excited. So there's an excitation happening when the material absorbs energy by means of heat, electrical energy, light, or chemical energy. So in order to discuss excitations of atoms and molecules simply, in simpler terms, we will use the idea of energy levels or energy states. So we have the lowest energy state called the ground state, and the next to that are the excited states. So you have the first excited state energy level, second excited state, third excited state, or the third excited energy level. So usually, if a material or an atom, for instance, is in the ground state, is in the lowest energy state, and it absorbs energy by means of heat, electrical energy, light, or chemical energy, it can go to an excited state. So for us humans, if we took this analogy to us, then for us humans, our ground state is when we are sleeping. That is our ground state. So when we are awake, maybe that's our first excited state. And we are eating, we are working, that's our second excited state, and so on. So if an atom or a molecule absorbs energy by virtue of heat, electrical energy, light, or chemical energy, it can transition. It will be excited to a higher energy state or higher energy level. So, for instance, in this case, it is excited to, or it transitions to the second excited state. So imagine a child eating too much sugar, too much candy. No, you will notice that the child will get excited, right? So, but eventually, the material or the atom will be excited. And in the process of de-excitation, so suppose the atom de-excites from the second excited state to the first excited state energy level. And in that de-excitation, it will spontaneously emit light at a specific energy and a specific wavelength. And the energy of this light actually is equivalent to the difference of the first excited state energy level and the second excited state energy level. So this difference. So spontaneous emission of light, of course, can lead to luminescence. One example of spontaneous emission of light can lead to luminescence. So the energy of this emitted light, again, is inversely proportional to the wavelength. The higher the wavelength, the lower the energy. So UV light has higher energy as compared to red light or blue light. because UV light have smaller wavelengths. So this is the most important part. The wavelength or the color of the emitted light during this transitions towards a lower energy state is actually specific to this certain energy level transition within a material. So you will notice that uh, by just studying the wavelength of light emitted by a material, you will know that you will know the type of the material, because the light emitted by that material is specific to a certain energy level transition. So it can be used to characterize that material. So an emission if you study the emission of light, it can characterize your material. So you will know what type of material it is. So let's now relate. What's the relationship between light and color before we go to spectroscopy? So the emitted light or reflected light or transmitted light from a material follows the additive mixing of colors. You must not be confused by this, because if you are studying photonics or optics or light in general, you must dispose of your ideas about uh, color mixing, because what we are taught in grade school about color mixing is actually the subtractive mixing of colors. That if you combine a yellow and a blue color, you will get a green color. If you combine a yellow and a red color, you will get an orange color. Or in terms of cyan, magenta, yellow, which are the colors of our printer inks, if you combine cyan and yellow, you will get green and so on. If you combine all of this, you will get the key color. The key color is usually black. So subtractive color mixing is only applicable in paints, pigments, or inks. And you must not use this analogy when you are dealing with light. So when you are dealing with light, you must use the additive mixing of colors. So in the additive mixing of colors, the primary colors are RGB, red, green, blue. So if you combine red and green light, you will produce yellow light. Here, if you combine a yellow colored pigment and a blue colored pigment, you get green. But actually, in terms of the wavelength of light emitted by these materials, you're actually subtracting yellow from blue. So blue wavelength minus the yellow wavelength, you'll actually get the green wavelength. That's a subtractive mixing of colors. So in light, we use the RGB, the additive mixing of colors. So red and blue makes magenta. So magenta, cyan, and yellow are the secondary colors. If you mix all of them in equal quantities, then you will get white. So if you have all of the colors from red, green, blue, and all of their combination, all of the other secondary and tertiary colors, of course you will get white. If they are all in equal quantities or intensities. The only way that you will get black is if there's no light at all. There's no red, there's no blue, there's no green. That's the only time you will get black. There's no light. So black is the absence of light. So if you have a material and it appears white, then that means that it transmits or it reflects or it emits all of the wavelengths, visible wavelengths in equal intensity. So it emits red, it emits green, it emits blue. So here is an example of a simulation showing these effects. So if you have no light, then what you perceive is black. If you only have a red light, then of course you see it as red. But if you have red and green, you'll actually get yellow light. And if you get all of the three in equal intensities, you will get white light. If you only have, say, full intensity of blue, equal intensity in green, and say half intensity of red, you will get something like a bluish light. If you have half of green and half of red and full intensity of blue, you will get some purplish color. And if you have half of everything, you will see some grayish color. So from these three color mixing alone, you can produce any type of color by controlling the intensity of the red, green, and blue emitted lights. So this is actually how all of our TVs and monitors and other appliances, display monitors work. So going back to the presentation, so if you have a material and you shine white light on it and it looks yellow, that means that it only emits red and green wavelengths, which makes red and green makes yellow. Meaning, in this material, the blue wavelength is actually absorbed, and only the red and green, which makes yellow, only the yellow wavelength is transmitted or reflected or emitted in the case of emission. So another example, if you have a blue object that appears to be blue under white light, so you shine white light on your object and it still appears blue, then that means that the red and green wavelengths are absorbed, meaning the yellow is absorbed, and only blue is emitted or reflected or transmitted by your material. So in general, the relationship between transmittance, absorbance, and reflectance is that they're all equal to 100% or 1. So if you have a material and you shine light on that material, the amount of light that is incident on your material is divided into some percentage of that will be absorbed, some percentage of that will be reflected, and some percentage of that will be transmitted. Transmitted means it will pass through the material. Okay. So this is an example of the absorbance spectra of metal orange. You have now discussed about absorbance spectrum in the previous lectures. So this is for metal orange. So the absorbance peak of metal orange is actually in the violet blue region, 466 nanometers, and in the UV region at 269 nanometers. So metal orange looks orange. So it's a liquid, it's a semi-transparent liquid that looks orange. So meaning the transmitted light that you see is orange. But if you'll notice from the absorbance spectrum, it actually absorbs violet or blue. So the RGB color wheel here will guide you in how to analyze transmitted and absorbed light. So if it's transmitting orange, then it's somewhere a mixture of green and red, not with the same intensity, but different intensities to produce orange. And that's actually, which means that if you transmit orange, then it absorbs the blue wavelength. That one. So as I've said earlier, TV and PC monitors or any display monitors uses the RGB technology. So they only actually have RGB pixels, and each of these pixel intensity can actually be controlled to emit a specific color in general that is perceived by our eyes. So this is a display screen magnified at 60 times so that you can see the pixels. So it's actually just a pattern of red, green, and blue pixels. Okay. So moving on to emission spectroscopy, which is our topic for this lecture. So emission spectroscopy basically analyzes or studies the different wavelengths or the spectrum of wavelength or light emitted by a material. So you have a sample. Your sample, it could be self-luminous or incandescent or luminescent, and it will emit light due to, again, these emitted wavelengths are due to energy transitions. It can emit red, orange, yellow, green, blue, violet light, or even infrared or UV light. Your spectrometer will now then detect these wavelengths and measure, and it will transmit this data into a computer for the computer to analyze this data and generate an emission spectrum. So as opposed to absorbance, in absorbance, your sample is actually not self-luminous, or it's different from the light source. So you have a light source, it's separate, your sample is here. And in contrast to emission spectroscopy, in absorbance spectroscopy or transmittance spectroscopy, the wavelength of light is actually controlled. So you shine light on your sample, but you do it one wavelength at a time, one color at a time, and you scan it, and you find if that specific wavelength is absorbed or transmitted by your sample, so which is your absorbing species, and then that will be detected by your photodetector. Now in emission, the light source is the sample, or the sample is the light source. So there's no middleman between the sample, which is your light source, and your spectrometer or detector. So in this case, the only difference is that if you want to convert this into an absorbance setup, you put an absorbing species in between here to absorb the emitted light, and you control the light one wavelength at a time in the case of absorbance. Now, each of these spectroscopic techniques have different purposes, but they can be both be used to determine, say, what type of molecules are in your sample, in the case of absorbance, or in the case of emission, what type of atoms are consisting your luminescent or self-luminous sample. So they can be both for characterization, to characterize your sample. So that one. So another thing that an emission spectrum can give you is that it can analyze what wavelengths of light are predominant. So for example, this is the spectrum of sunlight in space without the atmosphere as a function of wavelength. So you will notice that only 44% of light from the sun is actually visible. So this area here. So 7% UV, and the remaining 49% is above red. So you have infrared, microwaves, radio waves, Bluetooth, and so on. So that's one thing an emission spectrum can give you. So another thing that an emission spectrum can give you is, or can do, is it can analyze the composition of a light source. So this is the emission spectrum of fluorescent light. So this is only the light coming out of a fluorescent light bulb. So you will notice that there are peaks here, and each of these peaks corresponds to a specific emission wavelength, or it corresponds to a wavelength for a certain or specific energy level transitions within the material, as we have discussed earlier. So for example, the first, second, and third peaks correspond to mercury. So mercury emits actually UV light, but that's actually, most of that UV light are actually absorbed by the phosphor coating in your fluorescent light bulb. So this is now very small, but you will notice that this peak here, peak number 5, that's also for mercury. So it still emits visible light passing through the phosphor coating. So that one. And the peaks, the second peak here, the second high peak here, this is actually from the phosphors, from the white phosphor coating in your fluorescent light bulb. So fluorescent light bulbs are actually now obsolete technology because of LED technology, and it's actually hazardous because of the mercury. So, but from here, you see that the emission spectrum can give you what types of gases are emitting light. So here we can see it's mercury, and there's terbium, there's europium, and I don't know what I can read europium, argon, possibly argon, terbium, and so on. So those are phosphor. Some of these are phosphor coatings, and some of these are gases. So there's possibly argon and mercury gas inside your fluorescent light bulbs. So an emission spectrum can also analyze chemical reactions. So for instance, you have for example, in the glow stick example, you have two materials, and when these two materials react, they produce light. So, for instance, you have, say, luminol, and then when you react luminol with, I think, hydrogen peroxide, you will get a reaction which emits light or which emits chemiluminescence. So, it can analyze chemical reactions. It can also analyze the effects of varying the chemical compositions of the emitted light. So, this is an example of photoluminescence spectroscopy. So by varying the concentration of iron CO2, you get different photoluminescence intensities. So this is photoluminescence spectroscopy. So an emission spectrum can also be used in life science, in biology, say to classify organisms based on species, based on sex, or etc. So this is an example emission spectrum of the wavelengths emitted by different insects. Maybe one of this is fireflies. I don't know what is Diptera, Coleptera. So they have different species. So you can also use this to classify species based on, say, sex or based on age. So there have been researches about fireflies that depending on whether it's a female or a male, it emits different wavelengths of light, and also depending on the age of the fireflies, it can also the emitted light also varies in color or in wavelength. So that one. So this is bioluminescence spectroscopy. Let's focus on photoluminescence spectroscopy, more specifically on fluorescence spectroscopy. So this can be used to analyze at what excitation wavelength will be absorbed by the material, causing it to emit light at a lower energy, or at what emission wavelength will result given an excitation wavelength or light. So the absorption spectra of a material that is fluorescent is actually related to its emission spectra. So the absorption spectra is actually the excitation, the peak absorption or peak absorbance of the material is actually the excitation wavelength. So if you want to find at what wavelength a fluorescent material will you will use to excite that material, you will probably choose the peak absorbance in absorbance spectroscopy. And of course, the peak emission wavelength is related to the peak absorbance by the Stokes shift. So you can just actually predict the absorption and emission peaks of a fluorescent material. So of course, fluorescence spectroscopy is only used for compounds or materials that fluoresce, that emits light. So of course, if your material is not fluorescent, then you can't use fluorescence spectroscopy. But more or less, if your material is liquid, it will undergo some degree of fluorescence. So usually in fluorescence spectroscopy, the detector or your spectrometer is placed in 90 degrees with your excitation light source. So this is your light source, this is your sample here. In absorbance and transmission spectroscopy, you usually place your detector in line with your light beam and your sample. But since we are trying to quantitatively measure the emitted light due to photoluminescence or fluorescence, then we place a detector at a different angle. So usually it's a 90-degree angle. So if you want to measure both absorbance and fluorescence, then you can put your detector, one detector here, and for absorbance and transmittance, and your detector here for fluorescence or photoluminescence. So one application of fluorescence spectroscopy is in fluorescing quantum dots as biomarkers. It's actually fluorescence microscopy. But before you can uh, uh, use or go to fluorescence microscopy, you first need spectroscopy. You first need to determine what wavelength will I use to excite my fluorescent, in this case, fluorescent quantum dots, and what will be the expected emission wavelength. So that one. So they use fluorescent quantum dots as biomarkers to image cancer cells in a live mouse. So before you can go to microscopy, you first need to do spectroscopy. Simple experimental setup for fluorescence spectroscopy. You need, for instance, a higher energy light source such as a UV or UV laser or UV flashlight. If your sample is liquid, you put it in a cuvette, and then so you put your laser, shine your laser or UV light on top, and then measure the emitted or the fluorescent light at the sides of your cuvette or your sample, and transmit your data to the computer. But there are spectrometers which already have a built-in fluorescence function aside from the absorbance and transmittance. So I think this will be demoed to you after this presentation. Oh, so that's the end of my lecture. So I hope you learned something about emission, about fluorescence, about fluorescence spectroscopy in this lesson. And once again, I'm Jonathan Pimanigo, and I am now ready to receive your questions if you have some. So thank you for listening.